Today, we're going to be talking about degassing and why it's such an important step in aquaculture. In our business, we focus on providing solutions for recirculating aquaculture systems, or RAS. And these systems, by their nature, require us to remove specific things from the water, including solids and excess dissolved gases. The latter can pose a significant challenge. So let's talk about why this is important. Aquaculture systems, especially recirculating aquaculture systems and deep well or groundwater-fed systems, can accumulate various gases that, while normally present in the atmosphere, can become problematic when dissolved in water at high or low concentrations. While there are many different types of aquaculture production systems, the ones I mentioned have one thing in common. They involve moving water over time. This results in the introduction of air into the system, either through direct contact with the atmosphere or by pumping or drawing water through pipes or equipment. Also, depending on the source of your water, it may already contain elevated levels of some of these gases. As these gases dissolve into the water, they can reach concentrations that are much higher than what is found in the atmosphere. For example, normal atmospheric oxygen is around 21% by volume. However, fully saturated water can hold up to 8 milligrams per liter of dissolved oxygen. When this happens, gases can become toxic to fish and other aquatic organisms. This condition is known as gas bubble disease, or GBD. So let's look at how these gases get into the water and why degassing is so important. First, there are two main ways that gases can enter your aquaculture system. The first is through direct atmospheric entrainment. The second is through biological processes within the system. Atmospheric entrainment refers to air being drawn into pumps, pipes, or diffusers or being forced into the water through turbulent flow. Here we can see dissolved oxygen and nitrogen being transferred from the atmosphere into the water. As the water passes through the pump, pressure is reduced, which lowers the solubility of these gases. As a result, they come out of solution forming bubbles. You may have actually seen this before if you've ever run an air pump in a home aquarium. The air bubbles introduced through the air stone quickly become supersaturated with oxygen, which can then diffuse into the fish tank water. This is why some aquarists add air stones to increase the amount of dissolved oxygen in the tank. In commercial aquaculture systems, however, this is often a bad thing. There are several different mechanisms for removing air from a system. One of the simplest is a degasser. A degasser uses a packed tower to allow air to escape from the water by dissolving the gas back into the liquid. Some commercial systems use a vacuum degasser like this one here. This works by reducing the pressure of the water and allowing the gases to release into the venturi. Other systems use a sparging tower where compressed air is used to force the gases out of the water. Both of these methods are effective but typically require additional components and infrastructure to operate. Another method of removing dissolved gases is through the use of a surface aerator. A surface aerator is basically a giant waterfall that provides a large surface area for oxygen to escape from the water back into the atmosphere. The water cascades over the weir, and as it loses height, its velocity increases until eventually the dissolved gases reach equilibrium with the atmosphere, and then they can simply evaporate into the air. Surface aerators do not require any additional energy input, and they are passive systems. However, they do take up a lot of space, and they also rely on ambient conditions. That means that if there's no wind, the evaporation won't be as effective. Let's look at the second way gases can enter the system: biological processes. Gases can be produced by respiration by aquatic animals, decomposition of organic matter, or by bacterial processes such as denitrification. In general, most of these biological processes will produce carbon dioxide, oxygen, and nitrogen. Some can also produce hydrogen sulfide, methane, and ammonia. Again, the concern is that these gases can reach concentrations that are high enough to be toxic to the fish. For example, fish can respire up to 50 times more oxygen than the surrounding environment, meaning that if left unchecked, their oxygen consumption can quickly deplete the dissolved oxygen in the water. Likewise, decomposition of uneaten feed or fish waste products by bacteria can also consume dissolved oxygen. In addition, these bacteria can also produce carbon dioxide, hydrogen sulfide, and ammonia. Denitrifying bacteria can convert nitrate into nitrogen gas. This can be a good thing since it removes nitrate from the system, but it does produce nitrogen gas as a byproduct. Now, there are other processes that occur within an aquaculture system that can contribute to the amount of gas dissolved in the water. For example, gas exchange between air and water can occur through the surface of the water. If the system has a high surface area to volume ratio, this can be a significant amount. One of the most common examples of this is in ponds. Ponds have a large surface area compared to their volume, meaning that there is a lot of opportunity for gases to diffuse between the water and the atmosphere. Another process that can contribute to gas levels is the use of ozonation or other treatments that produce free radicals. Free radicals are highly reactive and unstable atoms or molecules that react readily with other compounds. Ozone, when decomposed by UV light, will produce free radicals that react with dissolved gases such as CO2, resulting in the release of oxygen. Free radicals can also react with ammonia, converting it into nitrogen gas, or react with sulfides, converting them into elemental sulfur. Finally, adding oxygen to the water through an oxygenator, or increasing or decreasing the temperature of the water, can also influence gas levels. This is because the solubility of gases is temperature dependent. For example, cold water holds more dissolved oxygen than warm water. So now that we understand how gases can enter the system, let's talk about why it's important to control them. First, excess dissolved gases can be toxic. Most fish and other aquatic organisms require dissolved oxygen for respiration. However, if the concentration gets too high, it can actually become toxic. For example, most fishy species need between 5 and 7 microL of dissolved oxygen to survive. However, if the concentration goes above 9 microL, it can actually start to affect their gills, causing damage and impairing their ability to breathe. This can lead to stress, decreased growth, and even death. In addition, high levels of carbon dioxide can also be harmful to fish. Most fish can tolerate up to 40 mg/L of carbon dioxide. However, if levels go above 100 mg/L, it can start to affect their ability to absorb oxygen, leading to stress and death. Aside from dissolved oxygen, other gases can also be problematic. Hydrogen sulfide, for example, can be toxic to fish even at low concentrations. Exposure to high levels can cause death within seconds. Ammonia is another gas that can be harmful to fish. Most fish can tolerate up to 1.5 mg/L of ammonia as nitrogen. However, exposure to high levels can lead to gill damage, decreased growth, and mortality. Second, supersaturated gases can form gas bubbles. If gases are present in water at concentrations above atmospheric equilibrium, the water is considered supersaturated. Supersaturated water is unstable and can release dissolved gases in the form of bubbles. This can occur when water is depressurized, for example, by flowing through a pipe or being pumped. The bubbles can cause physical damage to the fish by abrading their skin or gills, or they can block their gills, preventing them from obtaining oxygen. This condition is known as gas bubble disease or GBD. And finally, some gases can react with other compounds in the water. For example, carbon dioxide can react with water to form carbonic acid, which can lower the pH of the water. This can lead to a condition known as acid stress, which can impair the fish's ability to absorb oxygen and regulate their internal pH, leading to stress and death. So, as you can see, dissolved gases can pose a number of challenges in aquaculture. By controlling the levels of these gases, we can ensure the health and well-being of the fish and other aquatic organisms. Hi, this is your host with a presentation on the benefits of effective degassing. one of my favorite topics because it covers many things that affect fish health, production, and overall pond or aquarium health. There's 6 main points I want to cover. Number 1 is prevents gas bubble disease or GBD. Number 2, optimizes pH. Number 3, enhances oxygen uptake. Number 4, improves biofilter performance. Number 5, reduces stress. And number 6 is increased productivity. So let's go through these one by one. So number 1 is prevents gas bubble disease. This is the number 1 reason why we need to remove CO2 from our ponds and aquariums. In nature, there's always an exchange of gases happening between the atmosphere and the water, but the atmosphere has about 21% oxygen and about 0.4%. CO2 undersaturation causes an imbalance in the blood chemistry of the fish. When CO2 levels are too low, the blood becomes too alkaline. This makes the blood more caustic and damages the fish's ability to transport oxygen throughout their body. They also become stressed and their immune system suffers. Fish suffering from GBD may exhibit a range of symptoms depending on the severity of the condition. These can include listlessness, loss of appetite, abnormal swimming behavior, including gasping at the surface, lack of equilibrium, exophthalmia, which is bulging eyes, hemorrhages, internal organ damage, and ultimately death. Even mild cases of GBD can stunt growth and development, making fish slower to reach market size and ultimately reducing profits. Now, I actually have a separate video on how to identify and treat GBD. I'll link to that below so you can learn more, but as you can see, GBD has many negative effects. So the number 1 benefit of degassing is to prevent GBD by maintaining proper CO2 levels in the water. Number 2 is optimizes pH. Removing CO2 not only helps to prevent GBD, it also helps optimize pH. When CO2 is present in water, it reacts with H2O to form carbonic acid. As the concentration of CO2 increases, more carbonic acid is formed and the pH decreases. Conversely, when CO2 is removed from the water, less carbonic acid is formed and the pH increases. Therefore, degassing can be used to raise pH levels in aquaculture and aquariums. But keep in mind, if your water source already has a high pH, like an alkaline well, then degassing may actually lower the pH. In most cases, though, degassing will help optimize pH for nitrification, which is ideal between 7.2 and 8.5 pH. Number 3 is enhances oxygen uptake. As I mentioned earlier, in nature, the oxygen and CO2 levels in water are always changing and fluctuating. Because of this, fish are able to naturally uptake sufficient oxygen without any problems. However, in aquaculture and aquariums, we tend to add aeration to increase oxygen levels. But when CO2 levels are high, this can offset the added aeration. If CO2 levels are high, fish will find it harder to uptake oxygen. This is because when CO2 is present in water, it competes with oxygen for uptake by the fish. So if there's a lot of CO2, then oxygen uptake is reduced. Therefore, by removing CO2, fish can take up more oxygen even at ambient levels. You can actually calculate this by using a graph called a solubility curve. Number 4 is improves biofilter performance. For optimal performance of your biofilter, we need to maintain a good balance of bacteria. These bacteria perform nitrification, which converts toxic ammonia to less toxic nitrite and then to nitrate. The bacteria that perform nitrification prefer a more neutral pH range, around 7.2 to 8.2 pH. As mentioned previously, CO2 helps to optimize pH. Therefore, removing CO2 allows us to achieve this ideal pH range for nitrifying bacteria. This results in improved biofilter performance and ultimately better water quality. Number 5 is reduces stress. Like all living organisms, fish experience stress, and this can have serious implications for their health, growth, and survival. When fish are exposed to stressful conditions such as extreme temperatures, low oxygen levels, high stocking densities, poor water quality, handling, and transportation, they will become stressed. Chronic stress can weaken the immune system and make them susceptible to disease. In addition, stress can cause fish to stop feeding, which can lead to starvation and death. One of the causes of stress in aquaculture and aquariums is an imbalance of gases in the water. As mentioned before, when CO2 levels are too low, it can cause GBD, which puts stress on the fish. Similarly, when CO2 levels are too high, this can also cause stress by reducing oxygen levels and causing the fish to be constantly stressed from trying to obtain enough oxygen. Therefore, degassing can help reduce chronic stress by keeping gas levels within the optimal range. And number 6 is increased productivity. This one is pretty obvious but worth mentioning because it covers a few things. When fish are free of disease, they grow faster, require less feed, and produce more offspring, thus increasing productivity. As discussed previously, one of the main benefits of degassing is preventing GBD. GBD can cause a range of problems in fish, including stunted growth, reduced feed intake, and death. Therefore, by removing CO2 and preventing GBD, fish can grow faster and reach market size quicker. This ultimately leads to increased production for the farmer or hobbyist. In addition, degassing can also improve feed conversion by reducing stress and improving fish health. When fish are stressed, they require more feed to meet their energy needs. Therefore, by reducing stress, fish can convert feed into biomass more efficiently. This leads to cost savings for the farmer and improved productivity. Okay, so those are the main benefits of degassing. Now that you know how important degassing is, you might be wondering how to do it properly. Well, I have a video on that as well. I explain how to make a DIY degasser and how to use it effectively. So check out that video next. Thanks for watching. What are the harmful gases in aquaculture water? What effects do they have on fish? And how can we remove them from the culture system? Well, it just so happens that this is the topic of today's video. Let's get into it. First, we'll look at the 4 most common harmful gases found in aquaculture water. We'll then discuss their combined effects on fish. And finally, we'll cover ways to remove these gases, including physical, chemical, and biological methods. The primary harmful gases targeted for removal during degassing include nitrogen gas, carbon dioxide, hydrogen sulfide, and methane. Nitrogen gas is the most abundant gas in the atmosphere, making up about 78% of the air we breathe. It's relatively inert and usually doesn't pose a direct threat to aquatic life. However, it can become problematic in aquaculture systems through a process called supersaturation. When air is released into water, it can dissolve and become supersaturated with respect to nitrogen. This means that more nitrogen is present in the water than would be in equilibrium with the atmosphere at a given temperature. While this might sound beneficial, thinking that maybe your fish have an extra boost of oxygen because the air contains around 21% oxygen, it can actually be very detrimental. Supersaturation of nitrogen gas can lead to a condition known as gas bubble disease or GBD. Here's how it happens. When nitrogen gas becomes supersaturated in the water, it forms bubbles in the blood and other tissues of fish. These gas bubbles, called emboli, can obstruct blood flow, causing damage to organs such as the brain, heart, and gills. The affected fish may display erratic swimming behavior, become buoyant, and have difficulty maintaining their position in the water column. You may notice the eyes protruding, a condition known as exophthalmia or pop-eye. In more severe cases, the bubbles can erode the fins and tail, leading to their eventual loss. GBD caused by nitrogen gas supersaturation can be fatal to fish, although the exact mechanism and severity of the effects depend on various factors, including the level of supersaturation, the size of the air bubbles, and the species of fish. Nitrogen gas supersaturation can occur due to several reasons in aquaculture systems. One common cause is the direct entrainment of air, which can happen when water is pumped or drawn through the air, such as when water passes over a waterfall or is pumped from one location to another. Heating of groundwater can also lead to supersaturation, as warm water can hold more dissolved gas than cold water. Rapid changes in pressure, like those experienced during transport or when water is pumped at high speeds, can also cause nitrogen to come out of solution. Additionally, certain fish activities like spawning can create pressure changes that result in supersaturation. Now let's move on to the second harmful gas, carbon dioxide. Like nitrogen, carbon dioxide is also present in the atmosphere, but its concentration is much lower at about 0.04. Unlike nitrogen, carbon dioxide is more reactive and can have significant impacts on water chemistry and fish health. In aquaponics, carbon dioxide is actually beneficial as it's used by plants for photosynthesis. However, in fish culture alone, excessive carbon dioxide levels can be detrimental. In fish culture, carbon dioxide is produced primarily through the respiration of fish and other aquatic organisms, as well as the decomposition of organic matter by bacteria. The amount of carbon dioxide produced depends on factors like the number of fish in the system, their metabolic rate, and the amount of organic matter being decomposed. High carbon dioxide levels in fish culture can have several negative effects on fish health and growth performance. One major concern is the potential for reduced growth rates and chronic stress in fish. Carbon dioxide can interfere with the uptake of essential ions such as sodium and calcium, which are necessary for proper physiological functions, including osmoregulation and muscle contraction. The interference with ion uptake leads to imbalances in the internal chemistry of the fish, potentially affecting energy metabolism and growth. Furthermore, high carbon dioxide levels can impair the fish's ability to effectively process food and absorb nutrients. This can result in reduced feed intake, decreased digestibility, and ultimately slower growth. Carbon dioxide also plays a role in determining the acidity or alkalinity of water. When carbon dioxide dissolves in water, it reacts to form carbonic acid, H2CO3. Carbonic acid can then dissociate, releasing hydrogen ions, H+, and lowering the pH of the water. A decrease in pH makes the water more acidic. This process contributes to the formation of a more acidic environment, which can negatively impact fish health. In a highly acidic environment, the gills of fish can be damaged, impairing their ability to extract oxygen from the water. Additionally, the acidified water can increase the levels of heavy metals such as mercury, making them more toxic to fish. Moreover, an overly acidic environment can stress the fish, compromising their immune system and making them more susceptible to diseases and parasites. Another effect of high carbon dioxide levels is nephrocalcinosis, a condition characterized by the deposition of calcium in the kidney tissue. This condition can lead to kidney dysfunction and impaired osmoregulation in susceptible fish species. Now let's talk about the third harmful gas, hydrogen sulfide. Unlike carbon dioxide, which is relatively less problematic in aquaculture, hydrogen sulfide can be highly toxic to fish even at very low concentrations. Hydrogen sulfide is produced in aquatic environments under anaerobic conditions, meaning in the absence of dissolved oxygen. It's commonly generated during the decomposition of organic matter such as decaying plants or fish waste by sulfate-reducing bacteria. In aquaculture ponds or systems with stagnant water or poor circulation, hydrogen sulfide can accumulate in the bottom sediments where organic matter decomposition occurs. Over time, this can lead to a buildup of hydrogen sulfide in the water column, creating an unfavorable environment for fish. The toxicity of hydrogen sulfide to fish varies depending on factors like temperature, pH, and the duration of exposure. At low concentrations, it can still significantly affect fish health by impairing their ability to absorb oxygen and causing stress. Higher concentrations of hydrogen sulfide can quickly kill fish. Hydrogen sulfide has a distinctive rotten egg smell, so you might be able to detect it if you're near the culture system. And finally, let's discuss methane. Like hydrogen sulfide, methane is also produced in anaerobic conditions. It's often found in systems with high organic loads and poor water circulation, where sulfate-reducing bacteria break down organic matter. In aquaculture ponds, for example, methane can accumulate in the bottom sediments. While methane is generally less acutely toxic to fish than hydrogen sulfide, high concentrations can still be harmful. One way methane can negatively impact fish is by displacing dissolved oxygen in the water. This can create an oxygen-deficient environment, stressing the fish and impairing their growth and health. Additionally, methane is a potent greenhouse gas that contributes to global warming, so reducing its emissions is important for environmental sustainability. Now that we've covered the individual effects of each gas, let's talk about how they all interact within an aquaculture system. Often these harmful gases co-occur, making their individual effects more complex. For example, carbon dioxide and hydrogen sulfide can both be produced during the decomposition of organic matter. Therefore, measures to control one gas can help mitigate the other. Similarly, addressing the underlying issues such as low oxygen levels or high organic loads can help reduce the production of multiple gases simultaneously. Now that we understand the challenges posed by these harmful gases, let's explore methods to remove them from our aquaculture systems. One effective approach is to use degassing towers or waterfalls. These structures provide a surface for the gas to escape into the atmosphere, allowing for the replenishment of oxygen. Another method is aeration, which can be achieved by using pumps or diffusers to increase the amount of dissolved oxygen in the water. Additionally, optimizing system water flow can help prevent the buildup of stagnant water, where anaerobic conditions and gas accumulation are more likely to occur. Proper water circulation ensures that oxygen is evenly distributed and that organic matter is broken down more efficiently, reducing the production of harmful gases. Regular partial water changes can also help dilute and remove accumulated gases. By replacing a portion of the system water with fresh water, you can reduce the concentration of harmful gases and bring them back to acceptable levels. In addition to these physical methods, we can also employ biological approaches to control harmful gases. For instance, adding plants to the system can help absorb carbon dioxide through photosynthesis and release oxygen, improving water quality. This video we will discuss different methods and equipment used for degassing water. Stay tuned till the end, as we will be covering various types of degassing equipment available. Let's get started. Degassing is a process of bringing the concentration of gases in water into equilibrium with the surrounding atmosphere. In most cases, it is done to reduce the concentration of carbon dioxide and sometimes nitrogen in water. The main goal of degassing is to maintain healthy levels of dissolved oxygen and reduce the potential negative effects of high CO2 and N2 levels. In general, there are two approaches to remove gases from water. First, to increase the surface area of the water exposed to the air, which promotes gas exchange at the water surface and allows gases to escape. Second, to reduce the partial pressure of gases in water below their saturation point, causing them to come out of solution. Let's first talk about how increasing the surface area of water exposed to the air helps in removing gases. One of the most common and simplest methods is known as splash aeration or cascading towers. In this method, water is allowed to fall and splash over various packing media such as bioballs, plastic rings, or a series of trays or steps. This creates a turbulent flow of water, maximizing the water-air interface and facilitating the transfer of gases from water to air. Splash aeration is particularly effective at removing CO2 because of its ability to increase dissolved oxygen levels. Oxygen is essential for the health of most aquatic life, and removing CO2 is important because high levels can be toxic. This method is advantageous because it is relatively simple to construct and operate and requires low energy consumption. However, it does require a significant head or elevation to pump the water to the top of the tower. Additionally, the system can lead to heat loss due to the increased surface area of the water exposed to the air, which may require additional heating. Nonetheless, splash aeration is often combined with aeration, which involves adding oxygen to the water. This is typically done by introducing compressed air at the bottom of the tower or by using a surface aerator. By combining degassing and aeration, it is possible to reduce CO2 levels while maintaining optimal dissolved oxygen levels. Another approach to increase the surface area of water exposed to the air is using packed columns or stripping towers. In this method, water flows downwards through a column filled with random or structured packing media while air is introduced from the bottom. The movement of air and water counter-currently enhances mass transfer and facilitates the removal of dissolved gases. The third method we are going to discuss is vacuum degassers. Unlike the previous methods, which rely on increasing the surface area of water exposed to the air, vacuum degassers work by reducing the partial pressure of gases in the headspace above the water. When water is passed through a sealed chamber and a vacuum is applied, the partial pressure of gases in the headspace is reduced drastically. This creates a pressure differential that causes dissolved gases to rapidly come out of solution and into the headspace. Vacuum degassers are extremely efficient at removing all types of dissolved gases from water, making them suitable for a wide range of applications. They are particularly useful when very low gas concentrations are required, such as for research or for sensitive species. The main advantage of vacuum degassers is the precise control over gas removal that can be achieved by adjusting the vacuum level. However, they are less common in commercial aquaculture operations due to their high capital and operating costs associated with the vacuum pumps and the complexity of operation and constant monitoring required. Another method for degassing water is spray degassers. In this method, water is sprayed through nozzles into a tank filled with air, creating fine droplets that maximize the surface area exposed to the air. The water droplets quickly coalesce, releasing dissolved gases and forming larger droplets that fall to the bottom of the tank and are recycled back into the system. This process enhances gas exchange and reduces the concentration of dissolved gases in the water. Spray degassers are a relatively simple and low-cost solution for degassing water and are often used in industrial processes where large volumes of water need to be treated. They are particularly effective at removing CO2 from water and can also reduce N2 levels to some extent. However, they are less efficient than packed columns and can lead to the formation of aerosols, which may cause problems in sensitive environments. The final method we are going to discuss is aeration, which is primarily used to add oxygen to the water, but also has a secondary effect of degassing. Vigorous aeration, such as that provided by diffusers or surface aerators, promotes gas exchange at the water surface, allowing dissolved gases such as CO2 to escape and be replaced by oxygen. While not as efficient as other degassing methods, aeration can be a useful tool for maintaining acceptable levels of dissolved gases in aquaculture systems. To summarize, each degassing method has its own advantages and disadvantages. The choice of method depends on several factors, including the type and concentration of gases to be removed, the flow rate of water, space constraints, and budget. For instance, if the main goal is to reduce CO2 levels in a large volume of water, a packed column or spray degasser might be the best option. On the other hand, if very low levels of gases are required, a vacuum degasser may be more suitable. Ultimately, the most effective approach is often a combination of multiple methods tailored to the specific requirements of the system. Now let's look at different equipment available for degassing water. There are several types of equipment available for degassing water, each with its own advantages and disadvantages. We will cover 5 types of equipment in this video. As discussed earlier, splash aeration and cascading towers are one of the simplest and most common methods for degassing water. A typical splash aeration tower consists of a vertical cylindrical vessel equipped with an inlet for water at the top and an outlet at the bottom. Water is pumped to the top of the tower and allowed to flow over a series of trays or packing media, which can include bioballs, plastic rings, or other similar materials. The water cascades down the tower, creating a splashing sound and a fine mist that increases the surface area of the water exposed to the air. As the water flows over the packing media, dissolved gases such as CO2 are stripped from the water and released into the air. The effectiveness of the system depends on the design of the tower, the type of packing media used, and the flow rate of the water. The degassed water is collected at the bottom of the tower and returned to the system. Some systems may also include an air blower to force air through the packing media, enhancing gas transfer. Splash aeration towers are relatively low cost and easy to operate and maintain, but they can be bulky and require a significant head for pumping water to the top of the tower. Another option for degassing water is the packed column or stripping tower. A packed column consists of a vertical cylindrical vessel filled with packing media such as Raschig rings or other similar materials. Water is pumped to the bottom of the column and flows downward through the packing media while air is blown upward through the column. The countercurrent flow of water and air enhances gas transfer, allowing dissolved gases to be stripped from the water and released into the air. The degassed water is collected at the bottom of the column and returned to the system. Air is typically blown through the column using a blower or other similar device. Packed columns are more efficient at removing gases than splash aeration towers, but they are also more complex and expensive to build. A third option for degassing water is the vacuum degasser. A vacuum degasser consists of a vessel equipped with a vacuum pump and a gas-liquid separator. Water is pumped into the vessel, and a vacuum is created in the headspace above the water. The vacuum causes dissolved gases to be stripped from the water and released into the headspace where they are collected and vented to the atmosphere. The degassed water is collected at the bottom of the vessel and returned to the system. Vacuum degassers are the most efficient option for removing gases from water, but they are also the most expensive and complex to operate. The fourth option is the spray degasser. A spray degasser consists of a vessel equipped with nozzles that spray water into the air. The water is sprayed in the form of fine droplets, which increases the surface area of the water exposed to the air and allows gases to be stripped from the water and released into the air. The degassed water is collected at the bottom of the vessel and returned to the system. Spray degassers are less efficient than vacuum degassers, but they are also less expensive and complex to operate. Finally, the fifth option is aeration, which is primarily used to add oxygen to water but also has a secondary effect of degassing. An aerator consists of a device such as a diffuser or surface aerator that introduces air into the water. The air bubbles provide a large surface area for gas exchange and allow dissolved gases to be stripped from the water and released into the air. The degassed water is collected at the bottom of the tank or basin and returned to the system. Aerators are typically used in conjunction with other degassing methods to enhance gas transfer. There are many types of aerators available, including diffusers. These devices introduce air into the water through a series of small holes or diffusers. The air bubbles produced by the diffusers provide a large surface area for gas exchange, allowing dissolved gases to be stripped from the water and released into the air. There are several types of diffusers available, including internal and external diffusers. Internal diffusers are installed inside the water, typically at the bottom of a tank or basin, while external diffusers are installed outside the water and the air is bubbled through a pipe that extends into the water. Surface aerators. These devices are installed at the surface of the water and work by agitating the water, which increases the surface area of the water exposed to the air. This allows dissolved gases to be stripped from the water and released into the air. Surface aerators can be powered by motors or turbines and can be installed in various configurations, including vertical or horizontal orientations. The choice of aerator depends on several factors, including the size of the system, the depth of the water, and the desired level of aeration. Now we're talking about design considerations for aquaculture effluent, specifically settling ponds and basins for removing solids from the water. Now there's lots of ways to treat effluent in aquaculture, but ponds and basins are some of the most straightforward and cost-effective solutions. So that's what we'll focus on today. To start off, let's talk about the different zones that you'll typically see in a settling pond or basin. Then we'll move on to some more detailed design aspects. Okay, so starting with the inlet zone. This is where the flow comes into the basin, and it's really important that we distribute that flow evenly across the width of the basin. That way we avoid something called short-circuiting. Short-circuiting is when the water just flows from the inlet all the way to the outlet without spending any significant time actually settling in the basin. So we want to make sure that all the water passes through the basin slowly enough that those particles have time to settle out. So a few common ways to achieve good mixing in the inlet zone are using baffles, like these ones here, or a diffuser like this. These are just a few examples. There's other ways to do it as well. But basically, the goal is just to spread that flow out so that everything gets mixed and has time to settle. Next, we have the settling zone. This is the main body of the pond or the basin where the water slows down significantly so that those solid particles can settle to the bottom. After that, we have the sludge zone. This is the deepest part of the basin, and it's where all the settled solids, otherwise known as sludge, accumulates over time. Now, we don't want that sludge to get resuspended and go back into the water column. So, we want to make sure that the sludge zone is deep enough that it does not get stirred up by the water coming through the basin. But we also need to be able to access that sludge zone periodically and pump that sludge out or remove it in some other way. A common way to do this is with a center sump like you see here. Once the water has gone through the settling zone and the sludge zone, it flows into the outlet zone. The goal of the outlet zone is to collect the clarified water that's come through the basin, the stuff that hasn't settled out, and collect it at the surface and route it out of the basin. Again, we don't want to stir up the sludge that's settled in the sludge zone, so we typically put some sort of weir or submerged pipe in the outlet zone. That way, we're getting the clarified water from the surface and not disturbing the sludge. Some other design considerations include the overall shape of the basin. Most commonly, you'll see rectangular basins because they're relatively easy to construct, but you can see other shapes as well. Circular or even irregular shapes like this one with the baffle in the middle can work well too. And sometimes you'll see multiple basins in a series. 2 is most common, but you could have more than that, and you'll see those connected with piping. This way, the first basin will remove the larger particles that have a higher settling rate, and then those larger particles won't be in the water going through the second basin, allowing it to focus on removing the smaller particles. And lastly, another consideration is the quiescent zone. You'll typically see this in a raceway or a very long, shallow basin. And essentially what it is, it's just a section of the basin at the end where the flow really slows down to a stop and everything settles out before the final discharge. Now, the basic hydraulics behind how these systems work are fairly simple. We want to make sure that the flow coming in is distributed evenly across the basin. That's mostly achieved with the inlet structure. Once it's spread out, we want that water to slow down and allow those solid particles to settle out. So we're looking at minimizing the velocity of the water as it goes through the basin. The way we do that is by increasing the surface area. The water has to travel over a certain distance, and we can control that distance by the shape of the basin and the baffles, if any, that we put inside. And then we're collecting the clarified water at the outlet and routing that out of the basin. When it comes to sizing these basins or settling ponds, there's 2 main equations that we use. The first one is an overflow rate equation. An overflow rate is a common metric used for ponds and basins, and it's basically just the volume of water flowing through the basin divided by the surface area of the basin. Typical overflow rates for these systems range from 25 to 50 meters cubed per day per meter squared of surface area, so you can use that as a starting point. If you know the flow rate coming into your system, you can use that to calculate the surface area that you'd need for a given overflow rate, and you could also use that to calculate the volume of the basin. Another equation that's useful for these designs is the hydraulic retention time. Hydraulic retention time is the amount of time that it takes for a given volume of water to go through the system. For example, if you had a flow rate of 100 meters cubed per day and you had a basin with a volume of 250 meters cubed, your hydraulic retention time would be 2.5 days. So that means that on average, a given parcel of water would spend 2.5 days going through that basin. Typical hydraulic retention times for these systems are between 24 hours and 3 days. You could use either of those equations, or maybe both of them together, to size your basin. Another design consideration is sludge accumulation. We need to make sure that the basin is sized or designed in such a way that the sludge that accumulates in the sludge zone does not get too thick and it does not get too volatile. Like if it gets too thick, then the basin isn't going to work properly because it'll just be constantly overflowing, and we won't have enough room for the sludge to settle. And if it gets too volatile, then there's a risk of the sludge breaking down and releasing methane gas, which is flammable and could cause an explosion. In terms of sludge thickness, usually anything less than 1 meter is okay. And in terms of sludge age, that's just a fancy way of saying how long that sludge has been sitting in the basin before it gets removed. Usually, if you're pumping it out, you want to have a sludge age of less than 2 months. Another way to deal with sludge accumulation is to have some sort of sludge draw off pipe near the bottom of the sludge zone. This allows you to pump out the sludge without having to drain the entire basin. Now, we'll discuss the effectiveness and limitations of settling basins for wastewater treatment. We'll start with what they are good at, and then talk about their drawbacks so that you can decide whether it's appropriate technology for your situation. Let's begin with the positives. First and most important is solids removal. Properly designed and operated settling basins can be effective at removing a significant percentage of the settleable suspended solids in the incoming water. This is because they take advantage of gravity, which is a very reliable and cost-effective means of separating out heavier solids from the water column. Larger, heavier particles like sand, larger feed pellets, and larger fecal matter will settle out quickly. With some particle types having very predictable settling characteristics, it's possible to achieve high removal efficiencies for these types of solids with well-designed basins. Typical aquaculture operations will see 15 to 30% removal of total suspended solids with settling basins. But with optimal design and management practices, removal efficiencies can exceed 90%. Settling basins can also be used to remove other particulates such as debris or dead fish, which can help improve water quality and reduce odors. Another positive aspect of settling basins is their simplicity. They are relatively inexpensive to construct and operate compared to other wastewater treatment methods such as filtration or aeration systems. This makes them a suitable option for many aquaculture facilities, particularly those in developing regions such as Bangladesh, where land might be available and capital and maintenance budgets are limited. In addition to the low cost of construction, settling basins also require little to no specialized operation or maintenance beyond regular cleaning of the basin and its outlet. And speaking of low cost, another positive is that they are very energy efficient. Since they rely primarily on gravity and do not require pumping or other mechanical processes, their operational costs are very low. The energy required to run a settling basin is mainly associated with any ancillary equipment such as pumps for sludge removal or mixers to ensure proper mixing of the influent. However, even with these additions, the overall energy consumption is still much lower than that of other treatment methods. Settling basins are very versatile and can be adapted to a wide range of applications and site constraints. They can be constructed as either a single large basin or multiple smaller basins in series or parallel. They can be designed to operate at different hydraulic loading rates depending on the required level of treatment. And they can be constructed in various shapes and configurations such as circular or rectangular, with or without internal baffles or other structures. In addition, settling basins can be integrated with other treatment processes such as ponds or wetlands to enhance overall system performance. Their flexibility makes them an attractive option for use in various aquaculture settings. Another benefit of settling basins is that they contribute to nutrient removal by taking out the solid organic matter, which contains nitrogen and phosphorus. This is not as effective as other nutrient removal strategies, though, such as denitrification or phosphorus uptake by plants. But it's something that should be considered when evaluating the overall nutrient budget of the pond system. In addition to the direct nutrient removal, settling basins can indirectly contribute to nutrient reduction by improving water quality and reducing nuisance algal growth. By removing solids, the basin helps reduce the amount of organic matter and nutrients in the water that algae can utilize for growth. This can result in clearer water and a reduction in algae blooms, which can further improve water quality and aesthetics. Lastly, settling basins are well suited for aquaculture settings due to their ability to handle varying water qualities and flow rates. Aquaculture operations often involve fluctuations in water quality and production levels, which can impact wastewater characteristics. Settling basins are relatively robust and can tolerate variations in flow rate and water quality without significant impacts on their performance. This makes them suitable for use in dynamic aquaculture environments where conditions may change frequently. Now, let's look at the drawbacks. The first and most significant limitation of settling basins is their solids removal. As discussed earlier, settling basins are highly effective at removing larger, heavier solids, but they struggle to capture very fine colloidal particles such as plankton, clay, and other very small organic detritus. These particles have very low settling velocities and are easily carried in suspension by Brownian motion and other subtle water movements. As a result, settling basins typically cannot achieve high removal efficiencies for these types of solids, which can negatively impact downstream treatment processes or limit the overall performance of the system. Another limitation is that settling basins are not effective at removing dissolved nutrients such as ammonia, nitrate, and dissolved phosphorus. These forms of nutrients are not removed through settling and will pass through the basin mostly unaffected, requiring additional treatment processes to achieve desired effluent quality. Additionally, dissolved nutrients can still contribute to eutrophication and other water quality issues even if the concentrations are below levels that cause immediate concern. A third limitation is the large land area required. Settling basins typically require a substantial land area compared to other wastewater treatment options. The required footprint depends on factors such as the flow rate, hydraulic retention time, and desired level of treatment. However, this land requirement can be a significant constraint for facilities located in areas where space is limited or valuable. This can make it challenging to integrate settling basins into dense urban or industrial settings. Another issue is that settling basins can lead to sediment accumulation at the bottom of the basin, which requires regular desilting to maintain performance. Over time, solids that settle out in the basin accumulate at the bottom and can form a layer of sludge. This sludge can consume a significant portion of the basin's capacity and can create anaerobic conditions that lead to the release of nutrients or unpleasant odors. Therefore, it's essential to regularly remove the sludge to prevent these problems. However, desilting is often overlooked in favor of other more visible aspects of wastewater treatment, leading to reduced basin performance and other issues. Additionally, the sludge itself must be disposed of properly, which can be challenging and costly. Next is potential algae growth. If the water retained in the settling ponds is exposed to sunlight for extended periods, it can support excessive algae growth or algal blooms. This can occur when the settled water is not immediately discharged but remains in the basin, allowing algae to photosynthesize and reproduce. Algal blooms can negatively impact water quality by reducing dissolved oxygen levels, altering pH, and creating unsightly conditions. Furthermore, when the algae die, they decompose, releasing nutrients that can stimulate even more growth, creating a cycle of algal growth and decomposition. To mitigate this issue, it's crucial to minimize the time that water spends in the settling basin, especially during daylight hours, and to ensure that the basin is designed to prevent stagnant or overly slow-moving water that can promote algae growth. Lastly, it should be noted that settling basins are not suitable for applications where the wastewater contains a high concentration of floating solids or liquids. For instance, facilities processing oily wastewater or those with a high proportion of floating debris may find that settling basins are not effective at removing these substances. In such cases, additional treatment processes such as skimming or oil separators may be necessary before or after the settling basin to achieve the desired effluent quality. So, in summary, settling basins are an effective and efficient means of removing settleable suspended solids from aquaculture wastewater. Their simplicity, low cost, and ease of operation make them an attractive option, particularly in resource-limited settings. However, it's essential to recognize their limitations regarding fine particle removal, nutrient removal, and land area requirements. Carefully consider these factors and the specific characteristics of your wastewater stream to determine if a settling basin or another wastewater treatment method is more suitable for your needs. Hey, farmers! Now we're going to be talking about the principles of sedimentation. So this is how sedimentation ponds work and how settling basins work. And these are some of the most effective and most basic treatment processes used in wastewater treatment plants and aquaculture raceway clarification. So let's say we have this pipe here and we have this basin. What happens if we turn the water off? Well, the water is going to stop flowing. But once we turn the water back on, it's going to start filling up our basin at this rate, which is called the inflow rate. We can measure the volume of water coming into the basin and divide it by the surface area of the basin to find out what the flow rate is. Now, this flow rate is important because it affects how quickly we can fill up our basin and therefore how much time the particles have to settle. The lower the flow rate, the more time the particles have to settle. But there's also another principle that controls how quickly these particles settle, and that's the velocity of the water entering the basin. As the water approaches the basin, it has some kinetic energy due to its velocity. If we measure the velocity and multiply it by the density of the water, then we get the dynamic head of the flow. So if we have a very high velocity approaching the basin, then the kinetic energy of the particles is high, and this will keep fine particles suspended. And even if we wait a long time, they may never settle. In order to reduce the velocity of the water entering the basin, we use a structure called an inlet weir. An inlet weir is just a structure that breaks up the flow and reduces the velocity, so it makes the approach to the basin much more gradual. So instead of having a very abrupt change from this velocity to zero, we're going to have a more gradual change. So maybe the velocity here is very close to the velocity of the flow here, and by doing so, we're going to reduce the kinetic energy of the system. We want to reduce the water velocity as much as possible because this will allow us to remove the largest particles from the system. And it's not only the size of the particles that matters, but it's also their density. So if we have two particles of different sizes but the same density, then the larger one will always settle faster. For example, if I drop a basketball and a soccer ball at the same time, then the basketball will hit the ground first because it's bigger and has the same density as the soccer ball. Now, if I take a small soccer ball and a big basketball, then I drop them at the same time. Because the basketball is more dense, it'll hit the ground first. This means that although the basketball is bigger, the smaller, more dense ball will win. So the order in which these balls hit the ground is based on the product of their size and their density. Now, this product is called the hydraulic diameter, and if we multiply the hydraulic diameter by the overflow rate of the basin, we can find the settling velocity of the particle. So, if we have a particle with a hydraulic diameter that is smaller than the overflow rate, then the particle will not settle. And conversely, if we have a particle with a hydraulic diameter that is larger than the overflow rate, then it will settle. Now, the relationship between the hydraulic diameter and the overflow rate is known as the universal settling curve. And this can be used to predict the percent removal of a particle based on its size and density. Now, the formula for the universal settling curve is quite complicated and usually needs to be solved using an iterative method. But fortunately, we have tools that can help us find this out. Here is an online calculator that can help us determine the overflow rate given the hydraulic diameter. Just enter the hydraulic diameter and click on Calculate, and it will tell us what the theoretical overflow rate is. Another way of expressing the relationship between the hydraulic diameter and the overflow rate is to use a dimensionless group called the Reynolds number. If the Reynolds number is less than 0.2, then we have laminar flow. Between 0.2 and 2000, we have transitional flow, and anything above 2000 is turbulent flow. In laminar flow, the friction factor is very high, so we need a large diameter to transport a given amount of flow. In turbulent flow, the friction factor is very low, so we can get away with a much smaller diameter. For laminar flow, the friction factor is calculated by this formula, and for turbulent flow, it's calculated by this other formula. Now, the Reynolds number is also related to the overflow rate by this equation. And if we solve for the overflow rate, we get this equation here. This is the basis of the online calculator that we were using before. Let's say we have a particle with a hydraulic diameter of 0.02 millimeters. If we plug that into the calculator, we find that the overflow rate is 8 millimeters per minute. If we plug that into the Reynolds number equation, we get a value of 0.015, which is less than 0.2. So this tells us that the flow is laminar. So now we know that the flow is laminar. We can go back to our friction factor equations and use that to find the required diameter for a given overflow rate. So if we wanted to design a pipe that would deliver an overflow rate of 8 millimeters per minute, we would use the laminar flow equation and solve for the diameter. Doing so, we find that we need a pipe with a diameter of 17 millimeters. Now we know the diameter of the pipe that would give us an overflow rate of 8 millimeters per minute. We can also use this to find out what the hydraulic retention time is for a given volume and flow rate. To do so, we need to rearrange the overflow rate equation and solve for the volume. Doing so, we get this equation here, and this is the basis of the HRT calculator. You just need to enter the overflow rate and the surface area of the basin, and it will tell you what the volume is. Let's say we have a basin with an area of 1 square meter and an overflow rate of 8 millimeters per minute. If we plug those values into the calculator, we get a hydraulic retention time of 12.5 minutes. This means that if we have a constant flow rate into the basin, then the basin will fill up once every 12.5 minutes. And since the outlet is at the bottom of the basin, this also means that the average particle will spend 12.5 minutes in the basin before being removed. As you might have noticed, the calculations involved in designing a sedimentation basin can be pretty challenging. Fortunately, there are tools that can help us with this. Here is a spreadsheet that contains all of the calculations that we were doing today. If you download the spreadsheet, you'll notice that there are 3 sheets. The first sheet is where we input the hydraulic diameter, and it calculates the overflow rate and the Reynolds number. The second sheet is where we input the overflow rate and the surface area of the basin, and it calculates the hydraulic retention time. The third sheet is where we input the basin dimensions, and it calculates the volume. Now that we understand how the hydraulic diameter, the overflow rate, and the HRT are related, we can start designing our basin. The most important thing to remember is that the overflow rate controls the size of the particles that will settle, and the hydraulic retention time controls how efficiently these particles settle. If we choose a low overflow rate and a long hydraulic retention time, then we will be able to remove very fine particles. but this comes at a cost because we need a very large basin. For example, if we double the hydraulic retention time, we need to double the basin volume to maintain the same overflow rate. There is a trade-off between the cost of the basin and the quality of the effluent. In general, we want to keep the hydraulic retention time short enough to minimize the basin volume, but long enough to achieve the desired level of particle removal. For example, a hydraulic retention time of 30 minutes is long enough to remove 95% of particles larger than 0.02 millimeters. Here is a graph that shows the percent removal of particles as a function of hydraulic retention time. So, if we want to remove 95% of the particles larger than 0.02 millimeters, then we need a hydraulic retention time of around 30 minutes. But if we only want to remove 50% of these particles, then we only need a hydraulic retention time of 4 minutes. The hydraulic retention time can be increased by placing multiple basins in series. This is referred to as the number of stages. If we place 2 basins in series, then each basin will have half the hydraulic retention time of the overall system. And by adding more basins in series, we can increase the overall hydraulic retention time while keeping each individual basin small. Increasing the number of stages is an effective way to improve particle removal. However, there is a limit to how many stages we can use. Eventually, the basin becomes so large that it's no longer practical. Another thing that can affect particle removal is the presence of baffles. Baffles are structures that are placed in the basin to prevent short-circuiting. Short-circuiting is when the water flows from the inlet to the outlet without mixing with the water that is already in the basin. This can reduce the hydraulic retention time and decrease particle removal. Baffles can also increase the effective surface area of the basin, which can improve particle removal. The ideal baffle configuration will depend on the specific flow rate and basin geometry. However, in general, baffles are beneficial for particle removal. All right, thanks for watching. I hope this was helpful. See you next time. In today's episode, we're going to learn about how constructed wetlands work to treat aquaculture wastewater. So, if you're interested in learning more about constructed wetlands and their various applications, then be sure to watch this video till the end. So, let's get started. Aquaculture wastewater is typically rich in suspended solids and organic matter expressed as biochemical oxygen demand, or BOD, and chemical oxygen demand, or COD, as well as nitrogen in the forms of ammonia, nitrite and nitrate, and phosphorus. These pollutants can have adverse effects on the environment if discharged without proper treatment. So, constructed wetlands are one of the best eco-friendly ways to treat this wastewater. Constructed wetlands, also known as artificial wetlands, are designed to mimic the structure and function of natural wetlands to treat wastewater. They consist of a series of ponds or cells filled with a substrate such as gravel, sand, or soil, and planted with aquatic vegetation. The wastewater is passed through these ponds where pollutants are removed through a combination of physical, chemical, and biological processes before the water is discharged back into the environment. Now, let's look at how these 3 processes occur in the constructed wetland for aquaculture wastewater treatment. The first process is physical. As the aquaculture wastewater enters the constructed wetland, the water flows slowly through the substrate where several physical processes take place. One of these is sedimentation. For example, as the water flows slowly through the wetland, suspended solids such as uneaten fish food, fecal matter, and other organic debris settle out of the water column and onto the surface of the substrate. This process is similar to what happens in a settling basin, where the water is given time to rest so that the heavier particles can fall to the bottom. Over time, these settled solids are broken down by the biological processes in the wetland. But they must first undergo a transformation, such as being incorporated into the microbial biomass during bacterial overgrowth or being mineralized to inorganic forms such as carbon dioxide, water, and nutrients. The next physical process is filtration. The substrate in the constructed wetland, whether it's gravel, sand, or soil, acts as a physical filter that traps particulate matter as the water passes through it. This helps remove additional suspended solids from the water and further clarifies the effluent. In some cases, the substrate may also contain other materials such as coal or stone chips, as seen in a constructed wetland project in Bangladesh, where coal chips were used to treat shrimp farm wastewater. These materials can also contribute to the overall filtration process by providing additional surface area for solids to collect. Now, let's talk about chemical processes. The second category of processes that occur in a constructed wetland is chemical. These processes can help remove various pollutants from the aquaculture wastewater, including phosphorus and some heavy metals. One of these processes is adsorption. In this process, pollutants bind to the surface of the substrate particles. For example, phosphorus and some heavy metals present in the wastewater can be adsorbed onto the surface of gravel, sand, or soil particles in the constructed wetland. This reduces the concentration of these pollutants in the water and prevents them from entering the environment. Another chemical process that occurs in a constructed wetland is precipitation. This process involves the formation of insoluble compounds that cause pollutants to fall out of solution and settle to the bottom of the wetland. For example, when treated water passes through the wetland, certain chemical reactions can cause phosphorus to precipitate out of the solution as solid compounds. These compounds are then trapped by the substrate, reducing the amount of phosphorus in the water. Finally, another chemical process is ion exchange. During this process, ions are exchanged between the substrate or plant roots and the water. For example, the substrate and plant roots can absorb unwanted ions such as heavy metals from the water and release harmless ions in return. This can help remove heavy metals and other dissolved contaminants from the water. Overall, these chemical processes play a significant role in removing pollutants from aquaculture wastewater and protecting the environment from potential harm. Let's now look at the third category of processes, which are biological processes. Biological processes are the most important mechanisms for removing pollutants from aquaculture wastewater in constructed wetlands. These processes involve the use of microorganisms such as bacteria and fungi to break down and remove contaminants from the water. One of these processes is microbial degradation. In this process, bacteria and other microorganisms attached to the plant roots and substrate break down the organic matter in the wastewater. This breakdown can occur either aerobically or anaerobically depending on the availability of oxygen. Ultimately, the organic matter is converted into less harmful substances such as carbon dioxide, water, and biomass. This process helps remove the bulk of the organic pollutants from the water, including those in the form of BOD and COD. Besides this, there are two other crucial processes that occur in the wetland's aerobic and anaerobic zones. These are nitrification and denitrification, which help remove nitrogen from the wastewater. First, let's look at nitrification. It's the process by which aerobic bacteria convert ammonia, which is very toxic, into nitrite and then into nitrate. This conversion occurs in two steps. First, ammonia is oxidized to nitrite by the bacteria such as Nitrosomonas, and second, the nitrite is further oxidized to nitrate by other bacteria such as Nitrobacter. This conversion of ammonia to nitrate helps remove the toxic ammonia from the system while converting it to a less harmful form of nitrogen. The presence of oxygen is essential for these processes to occur, which is why they happen in the aerobic zone of the constructed wetland. Interestingly, the aquatic plants in the wetland can contribute to the oxygen required for nitrification as they release oxygen into the water as a byproduct of photosynthesis. This can help support the growth of nitrifying bacteria and enhance their ability to convert ammonia to nitrate. The second process is denitrification. This process is carried out by anaerobic bacteria in the oxygen-depleted or anaerobic zone of the constructed wetland. In this process, nitrate is converted to nitrogen gas, which is then released into the atmosphere. Another biological process that occurs in the constructed wetland is plant uptake, also known as phytoextraction. In this process, the aquatic plants in the wetland absorb nitrogen and phosphorus from the water for their growth. The plants then store these nutrients in their tissues, removing them from the water column. This process can help reduce the concentrations of these nutrients in the water and prevent them from entering the environment. The aquatic plants in the constructed wetland can help transfer oxygen to the root zone and provide surface area for microbial growth. This can help create an environment that is more conducive to the biological process that remove pollutants from the water. Additionally, the roots of the plants can also contribute to the removal of pollutants through ion exchange and adsorption processes. Overall, these biological processes play a crucial role in removing pollutants from aquaculture wastewater and protecting the environment from potential harm. In our last video, we talked about the basic principles of how sedimentation ponds and settling basins work. In this one, we'll discuss some of their many applications in aquaculture effluent treatment. Sedimentation ponds and settling basins are widely used in aquaculture for treating wastewater or effluent coming from different production systems. There are many different ways that they can be applied depending on the type of production system, the desired level of treatment, and local conditions. So let's talk about some examples. The first and probably most common application is in flow-through systems. Flow-through systems are those where large volumes of water are exchanged with the environment every day, such as open ponds, raceways, or flow-through tanks. In these systems, treated discharge water is released into natural waterways and therefore must meet certain quality standards to avoid adverse impacts. In many cases, this means removing solids since they can carry with them nutrients, organic matter, feed, and other contaminants which, if discharged in high amounts, can cause eutrophication and other problems in receiving waters. Sedimentation ponds and settling basins are therefore commonly used in flow-through systems to clarify the discharge water before releasing it back into the environment. The required size of the pond will depend on the concentration of solids in the water and the desired level of treatment. Typically, a pond will need to be filled at a rate equal to 10% of the production system volume per day to allow sufficient time for solids to settle. For example, if you have an earth-lined pond with 1,000 cubic meters of water, you would need a 100 cubic meter sedimentation pond. Since we often want to remove as much of the excess nutrients and organic matter as possible, ponds are sometimes operated in series so that the overflow from the first pond is treated by a second pond, which provides additional treatment. A second important application is in pond aquaculture. Pond aquaculture refers to systems where ponds are drained and refilled periodically during harvesting, or when the ponds are cleaned. During these events, large amounts of water must be transported out of the ponds either through pipes or by pumping. This process can stir up bottom sediments and other solids that can cause problems in the receiving water body if dumped directly. Therefore, sedimentation ponds and settling basins are commonly used to treat water drained from ponds during these activities. They capture solids, preventing nutrient and organic matter pollution of receiving waters. It should be noted, though, that many existing catfish ponds already function as de facto settling basins due to their elongated shape. Elongated earthen ponds have been shown to effectively trap solids that would otherwise be carried out of the pond during drainage events. Still, additional settling capacity could help improve water quality in the receiving stream and may be desirable in situations where high-quality water is needed for reuse or when water is being drained to a nearby wetland, which may not have enough time to naturally clear the water of solids. Another application is in recirculating aquaculture systems, or RAS. RAS typically use more sophisticated mechanical filters to remove solids from the water, such as drum filters. These systems are generally more expensive to build, but allow for more precise control over water quality and make it possible to reuse water within the facility. In these systems, sedimentation ponds and settling basins aren't needed to remove suspended solids from the water, but can still play a role. First, if the raw intake water contains high levels of suspended solids, then a basin may be used for pretreatment before the water enters the main system. Second, in RAS, the water generally needs to be clarified before being discharged to the environment. Therefore, a settling basin can be used for polishing the effluent after passing through the main treatment system. Third, in RS, there are several points where a settling basin can be used to handle concentrated waste streams. Clarifiers, for example, are used to remove uneaten feed and fish waste, as well as any excess algae grown for use as a protein-rich water reuse. Clarifier sludge has a high concentration of solids and organic matter, and can be pumped to a settling basin to allow the solids to settle before being returned to the main system as clean water or discharged to the environment. A similar situation exists with sludge drains, which collect excess solids and organics that have settled out in the system and need to be removed. By pumping them to a settling basin, the volume of the sludge can be reduced before it's disposed of. In addition to these uses, settling basins can also be used for sludge thickening in conjunction with other mechanical filters. When filter backwash or sludge drains are pumped to a settling basin, the resulting sludge often has a low concentration of solids and a high water content, which makes it difficult to handle and dispose of. If the sludge is allowed to settle for a longer period of time, however, the small particles will settle out, creating a sludge with a higher concentration of solids and lower water content that is easier to handle and dispose of. In summary, there are many applications for sedimentation ponds and settling basins in aquaculture. Their use depends on factors like the production system, desired level of treatment, and local conditions. As always, careful consideration should be given to the specific site and objectives prior to construction. Welcome back to my video. Now, we're going to talk about the different types of constructed wetlands that can be used for aquaculture. In our previous video, we talked about what constructed wetlands are and how they work. So before we dive into this topic, if you haven't watched that video, I highly recommend you to watch it so you understand some of the basic concepts. You can find the link to the video in the description below. Now, the two main types of constructed wetlands for aquaculture are classified based on how the water flows through them. And there are many different ways of classifying these systems, but we'll keep it simple today and just look at the two main ones. So the first one is called the free water surface constructed wetland, and the second one is called the subsurface flow constructed wetland. Now, the free water surface constructed wetland resembles a natural wetland where water flows above a soil substrate and can be seen on the surface of the wetland. This type of wetland has emergent vegetation such as cattails, reeds, and water hyacinth growing out of the water. These plants have special adaptations to survive in aquatic environments and play a crucial role in wastewater treatment by removing pollutants from the water. They absorb nutrients like nitrogen and phosphorus through their roots and stems, which helps to reduce eutrophication and improve water quality. These plants also provide food and shelter for wildlife, making the constructed wetland a valuable habitat for birds, fish, and other animals. The free water surface constructed wetlands are simple to build and therefore usually have low construction costs. They are typically constructed using locally available materials, making them an attractive option for use in remote areas. They also have an aesthetic appeal and can enhance the landscape, which makes them suitable for use in areas where visual amenities are important. Now, the free water surface constructed wetlands are effective at removing organic matter, nutrients, and other pollutants from aquaculture effluents. The wetland's vegetation absorbs dissolved oxygen from the air and releases it into the water, which helps to increase the amount of dissolved oxygen available for aquatic life. This increased dissolved oxygen levels can help to improve the growth and health of fish and other aquatic organisms. However, free water surface constructed wetlands also have some drawbacks. For example, they require a relatively large land area, which may not be available in all locations. They can also be prone to mosquito breeding and odors from the decaying organic matter in the water. Additionally, while they are effective at removing organic matter and some nutrients, They are generally less efficient at removing nitrogen than subsurface flow constructed wetlands. Overall, free water surface constructed wetlands are a suitable option for aquaculture operations, where large areas of land are available and basic pollutant removal and habitat creation are desired. They are relatively easy to construct and maintain, making them a good choice for small to medium-sized aquaculture operations. Now, let's take a look at the subsurface flow constructed wetlands. Subsurface flow constructed wetlands. The water flows through a bed of gravel or sand below the surface of the wetland where the plants are rooted. Unlike free water surface constructed wetlands, the water surface is not visible in subsurface flow constructed wetlands. Instead, the water moves through a series of pipes or channels that are filled with the gravel or sand media. The plants are planted in the media and their roots absorb the pollutants in the water. There are two types of subsurface flow constructed wetlands: horizontal subsurface flow and vertical flow. In horizontal subsurface flow wetlands, the water flows horizontally through the bed of gravel or sand. In vertical flow wetlands, the water flows downward through the media. Horizontal subsurface flow constructed wetlands. In a horizontal subsurface flow constructed wetland, the water flows horizontally through a bed of gravel or sand. This type of constructed wetland can be used to treat a wide range of pollutants, including organic matter, nutrients, and heavy metals. The horizontal subsurface flow constructed wetland can provide several benefits for aquaculture operations. First, they are less prone to odor problems and mosquito breeding compared to free water surface constructed wetlands. This is because the water is not exposed to the air, which reduces the amount of volatile compounds that can cause odors and provide habitat for mosquitoes to breed. Second, horizontal subsurface flow constructed wetlands are effective at removing TSS and BOD from aquaculture effluents. TSS, or total suspended solids, refers to the amount of solid particles suspended in water, while BOD, or biochemical oxygen, demand measures the amount of oxygen required by microorganisms to break down organic matter in water. By removing these pollutants, the constructed wetland can help to improve the quality of the water released back into the environment. However, horizontal subsurface flow constructed wetlands also have some limitations. They can be prone to clogging, as the media can become compacted or overgrown with vegetation, reducing the flow of water through the system. This can lead to a decrease in the effectiveness of the constructed wetland at removing pollutants from the water. Additionally, horizontal subsurface flow constructed wetlands are not as efficient at nitrification compared to vertical flow constructed wetlands. Nitrification is the process by which ammonia in the wastewater is oxidized to nitrate. This is important because ammonia is toxic to fish and other aquatic life, while nitrate is much less toxic. Vertical flow constructed wetlands. A vertical flow constructed wetland is a type of subsurface flow wetland, where the water is intermittently dosed onto the surface of the wetland and flows downwards through the media. This type of wetland is particularly well suited for treating high-strength wastewaters such as those produced by aquaculture operations. Vertical flow constructed wetlands offer several advantages over horizontal subsurface flow constructed wetlands for aquaculture applications. First, vertical flow wetlands have a smaller footprint than horizontal subsurface flow wetlands or free water surface constructed wetlands. This makes them an attractive option for aquaculture operations where land is at a premium. Second, vertical flow wetlands are more efficient at transferring oxygen to the water, which makes them more suitable for nitrification. This is because the large surface area of the media provides ample opportunity for oxygen to dissolve in the water. Third, vertical flow constructed wetlands are less prone to clogging than horizontal subsurface flow constructed wetlands because the media is constantly being replenished with fresh water. This results in less accumulation of fine particles that can cause clogging. Despite these advantages, vertical flow constructed wetlands also have some limitations. They are more complex to operate than horizontal subsurface flow constructed wetlands because the water needs to be intermittently dosed onto the surface of the wetland. This can be challenging to manage and requires more sophisticated control systems. Additionally, vertical flow constructed wetlands are generally more expensive to construct than horizontal subsurface flow constructed wetlands because they often require pumps to dose the water onto the media. Hybrid systems. Some aquaculture operations may use hybrid systems that combine both vertical and horizontal subsurface flow constructed wetlands in series. For example, a vertical flow constructed wetland may be used for nitrification, followed by a horizontal subsurface flow constructed wetland for denitrification. This can be an effective way to maximize the removal of pollutants from the wastewater while minimizing the footprint of the overall system. In conclusion, there are various types of constructed wetlands that can be used for aquaculture, each with its own set of advantages and disadvantages. The best type of constructed wetland for a particular aquaculture operation will depend on factors such as the strength and volume of the wastewater, the available land area, and the budget for construction and maintenance. Proper design and operation of the constructed wetland system are essential to ensure optimal performance and maximize the removal of pollutants from the wastewater.